Okay, so if you're absent today, it's 5:20 on Tuesday. We're going to do some stuff on simple harmonic motion. I am going to take the students down to the rotunda for a little field trip. I'll pause the recording there for us. And then if you are absent, you would have an investigation to be able to work on. You'll see that on the classroom page. Let's go ahead and begin. All right, so we are in this location in your note packet. So yesterday we talked through, Molly, you missed this. You do need to choose 3 or 4 of those things that you'd be interested in doing a presentation on. This would be the end of the unit project. We'll probably choose that topic tomorrow. Okay, so if you're present tomorrow, you'll be choosing that particular topic. If you're gone, you'll have to just pick what's remaining from that list. Okay, so we'll do the wheel of names to be able to identify which project you want to be able to work on. All right, so we went through this stuff yesterday, and again, if you were gone, make sure that you're watching the video for that. And then today what we want to move into is looking at this thing called simple harmonic motion. Something to refresh your memory on. That asterisk means it's not going to be on a test or a quiz. It is here primarily to serve as a foundation for understanding oscillations, but also many cases students are going to be working on projects that involve some of these things. So some of this is to lay that foundation. SHM is due to a restoring force that's directly proportional to the negative displacement from equilibrium. Equilibrium is the concept that we talked about in our first unit where the forces add to 0. So I have a demonstration for us up on the front. If you're watching this as a video recording, it's hard to see these presentations, but I have a cart being held in an equilibrium position with 2 springs on either side. On my left is a series of springs, that'd be your right, that's trying to pull that thing this way. On this thing, on my right, your left, is a series of springs that's trying to pull that way. When I look at the forces acting on that object, they add to 0. Now, when I pull this thing to my left, your right, the spring here pulls less hard than it did before. This spring up here pulls more hard. So there's a force, harder if you will. There's a force trying to bring it back to equilibrium. Now, when I let it go, it gets to the equilibrium position. It has inertia, so it continues on. Now I have a spring on this side that's pulling harder than it was before. That spring is pulling less hard. So now it's trying to bring it back to equilibrium again. And when I let it go, you'll see that it oscillates to and fro. That oscillation is exactly the same thing as my hand is going through, except now my hand is connected to a spring that allows that energy to travel as a waveform. So anything that's moving back and forth oscillating, if its restoring force is proportional to the negative displacement from equilibrium, it would be going through something called SHM. I could write this as an equation. I can write it as an equation. I just can't use the mouse for that. All right, so the equation looks like that. F is equal to negative kx. Now, that equation is what's called Hooke's law. Hooke was a contemporary of Newton. So, Brody, I'm going to have you sit at one of the normal seats. I don't want you to sit there. That way your phone is in the appropriate spot over there. I want to be able to look up on the bin and see up through 16 because we have 16 kids in here up to that point. And so make sure your phone's in the appropriate spot. Thank you, guys. Again, folks, occasional reminders, but I really don't want to have to remind you every day for that. Okay, just take care of the phones. Okay. Hooke's law, F is equal to negative kx. The negative means restoring. I wish I could write on this. Apparently I can't. But the negative means that it is a restoring force. It's trying to seek equilibrium. Okay, I want to look at this in terms of energy. So this is a little bit of review for you from our mechanical energy unit. It's good for the review for the final exam. Here is a picture of the mass in a spring oscillating to and fro. We have various forms of energy that we could fill these energy pies in with. And I want to type these things since I can't write really well. So we could use E for elastic potential energy. We could use K for kinetic energy. And we could use G for gravitational potential energy. So we have these forms of energy that we could use. Will you take a moment and see if you can figure out what forms of energy or energies belong in each of these energy pies based on where this thing is in its cycle? Just take a moment and see if you can do that. Elastic is energy stored in the spring, kinetic is energy of motion, and GPE is energy of position in a gravity field. So which forms of energy belong in each one of those pies? Take a moment and see if you can do that. If you're trying this from home, you should try that as well. Fill in each of those pies with the form or forms of energy based on its location. Okay. Hopefully that little restoring will allow me to write on this. So I'm hoping I had a chance to be able to try that. Let's see if this works. And it does. Far to the left, it's elastic potential energy. So that's energy stored in the spring for that oscillator. When I get far to the right, it's back to elastic. So at the end points, it's all elastic energy. Of course, where that energy is transforming, as it goes through the equilibrium position, it's being converted to kinetic energy. So what I have is elastic going to kinetic, kinetic going to elastic. And if I look at any location along this thing, you notice that that bottom mass is not at the end point, it's not at the equilibrium position. I could add up the total amount of energy, and I get the same as what I started with. So how much energy I have at each of those locations depends on where I'm located. And so the sum total of K and elastic should add to the top. Now, I want to take you guys and look at a pendulum, but instead of setting up a pendulum like I have here, I'm going to take you down to the rotunda and to be able to look at something called the Foucault. So we're going to do a little field trip. You need that stopwatch. So someone at your table is going to be doing some timing for me, and then we're just going to go down to the rotunda for a little bit, and then hopefully from there we can do some measurements based on determining periods and frequencies. All right, so I'm going to pause the video. Okay, so we're heading on back from our trip down to the rotunda to measure the period of the Foucault pendulum. And so timing is back on. So while we're regrouping here, I want to talk about how to do that period measurement from those times. So you had 5 cycles, and what I'd like to do is I'd like to get the time that you had back there again. Whoever the timer was. 33.56 seconds. For this table?
33.63.
33.63?
Yeah.
And I know model years didn't work. That's okay.
33.94.
33.94. Now, when I take those and add them up, divide by 3, I get the average time for 5 cycles. And even though there's some error there, we've reduced the amount of error due to the fact that we measured 5 of those. So the average value, divide that by 3, and I get about 33.71. And if I divide that by 5, what I get is the amount of time per cycle. So about 6.7 seconds. Now, I'm going to use that value of 6.7 seconds to show you how to calculate the actual length of that pendulum. So I heard some numbers, most everyone overestimated. So I think I heard as high as 20, somewhere in that area. Mr. Ferris down there and the officer was saying in the neighborhood of 17 to 20. All of those are overestimates. I'll show you how to do that calculation. If not today, we'll do that tomorrow. What I'd like to do is, instead of looking at bar or pie charts for elastic energy for that mass in a spring, I want to do line graphs for mechanical energy for a pendulum. So again, we have EPE, KE, and GPE, except for a pendulum, we don't use elastic energy, we use gravitational. I'm going to ask if you guys can see if you can't determine what the energy looks like as a line graph for a pendulum as it swings to and fro. Give it a go, see if you can do it. These are going to be line graphs. Try it. If you're watching this from home, you should try that as well. So at the far left and far right, instead of it being elastic energy, it's going to be gravitational. So at the far left, I'm going to use green for gravitational. So the gravitational potential energy would look like this, and if it's a smooth curve, it would look like a parabola. So that would represent gravitational. So this is GBE. Now, since the total mechanical energy, TME, is a constant, let's use red for kinetic energy. Then the kinetic energy would basically be a mirror image of that, such that the total amount of energy stays constant. And so that would be your graph of energy as a function of position for a pendulum. Again, the TME stays constant. As I lose gravitational potential energy, it gets deposited in kinetic energy. At this point here, it has inertia. It doesn't have any energy trying to move it back to position, but it has inertia, so it continues on until the gravitational potential energy will sort of bring it back to that position. So it oscillates to and from. Now, again, most of this stuff on this page here is an asterisk, which means that you're not going to be responsible for this on a quiz or a test. It's more foundation building. This next page, there's no asterisks except for those things that are hidden in those bars. So you have to know these terms. We need to be able to measure simple harmonic motion. The first one is the maximum displacement from equilibrium. That's called the amplitude. So I think it was Landon that pulled that thing all the way back, and I had you pull that pendulum from the middle position up to that bar. That would be the amplitude. So it's maximum displacement from equilibrium. The SI unit would be the meter. If this were a more advanced math class, we would use the radian if we were measuring angles. You are not going to use the radian as an angle measurement for us here. So the radian would be if we were to measure the amplitude for a pendulum. It's not going to be for us. The period is the time it takes to complete a full cycle. You guys measure the period of that Foucault using that stopwatch. The SI unit for this, again, you need to know the units for these values. The SI unit is the second. How long does it take to complete a cycle? And then finally, another one that people will confuse with the period is something called the frequency. Frequency is how many cycles it takes to complete, or how many cycles it completes in a unit of time. That time is usually a 1 second interval. The unit for that is what's called the hertz. How many cycles completes per second? Now, the frequency and period are reciprocals. What that means, I could write that as an equation. The period is something that you guys measured with the stopwatch. Frequency would be the reciprocal of that. So how I would write that as an equation is I could say that T is equal to 1 over F. Or I could say that frequency is 1 over T. They are reciprocals. So if I know one, I can determine the other. I want to take a moment and refresh your memory on the speaker that you guys built. That speaker looked like this. And then you had that little magnet down in here and so forth. That thing was set with a frequency of 1,000 hertz. So that tone that you were generating was a 1,000 hertz frequency. If I wanted to find the period, how long it took for it to go up and down just once, I would do 1 over 1,000. And that would be 0.001 seconds. So the amount of time it took for that speaker to go up and down once was a very short amount of time, 0.001 seconds. Too fast for us to see, but you can certainly hear that. Now, I'm not going to show you these equations just yet. The period of a pendulum is what I would use, that equation is what I would use to calculate the length of that pendulum. I'm going to do that with you tomorrow. What I'd like to do for the remainder of time is have you work on a lab that determines what factors affect the period and frequency of an oscillator. Now I have a mass and a spring set up here. This is a vertical one as opposed to a horizontal. When I set this thing into motion, it's going to vibrate up and down vertically instead of horizontally. If I wanted to determine the period, I just measure the time it takes to complete a cycle. If I wanted to determine the frequency, I would count how many cycles I complete in a certain amount of time, and I would calculate it that way. I could change things. Like I could change the mass of this thing from a lower mass to a higher mass. And when I hang this thing higher mass on there, you can see it stretches it further, and then I can set it into its vibration. And clearly you can see that its period seems to be affected there. What I'm going to have you guys do is I want you to run a simulation on your Chromebook that helps you investigate the factors that will determine or relate to the period or frequency of an oscillator. So I'm going to keep the video recording for a moment so that if you're having to watch this from home, you can see this as well. If you would open up your Chromebook, please. Okay, so second hour classwork, the lab Mass on a Spring Interactive. So I'm going to give you a sheet to be able to do this work on, but this will give you the interactive to be able to access it. So when you open this thing up, it's going to take you to a interactive on something called the physics classroom. If you're doing this from home or watching this from home, you will need this copy. Obtain this thing from me when you return to class. Okay. So record all answers on this sheet, please. I'm going to show you how to do one of these calculations so that you can copy that process for the other things that you'll test. All right. Put your name on it. Purpose is to determine what factors affect the frequency and period of a vibrating mass in a spring and state the relationship between those variables and the frequency and the period. So you're going to go to this site here. Getting acquainted, it just tells you to just play with it a little bit. I'm going to show you some things that you can adjust. If I want to change the spring stiffness, so up here I'm just looking at spring 1. If I make it a really lightweight spring, so something that might be very, very light, so it doesn't have a very strong stiffness, I could move it that way. If I change it this way, I'm making that spring a lot stiffer. So if I were to use something like a shock or strut system in my cars, it's going to be a very, very strong spring. If I'm going to use something that might be weighing maybe a bag of apples at Meijer, it's going to be a lighter weight spring. Okay, so the spring stiffness can be adjusted like so. I can adjust either the left or the right. You can probably just use one of these is fine. Damping, I would suggest that you keep the damping down to 0 so that it doesn't decay with its energy. So keep the damping down low. And then, of course, I have different masses that I can hang on this thing. Let's place this thing right here. I'm going to allow this thing to vibrate back and forth. And so what I'm going to do is I'm going to use the start button. And again, you're probably going to do this along with me for this first one. If I want to measure the period of this or the frequency, I'm going to hit the start button, and that's going to record the height as a function of time. Now, the height is fine. I could also look at the velocity, but in reality, just one of those graphs is sufficient. So what I see here is that this thing has gone through, I want to count the number of cycles. So when I go to count the cycles, I'm going to look at how many of these things are completed in this amount of time. So that's where I start. That's 1 cycle. That's 2 cycles. That's 3. That's 4. That's 5. And it looks like it's almost 5.5 cycles. So I would go through and say that the number of cycles is about 5.5. And the amount of time is 6 seconds. So if I want to get the frequency, I would go 5.5 cycles divided by 6 seconds. And my calculator will give me that. Again, you're going to need a calculator to complete these things, or just use the calculator on your Chromebook. If I take 5.5 divided by 6, I get 0.92 hertz. So that's how I calculate the frequency for that thing there. I count the number of cycles, Start there, that's 1, 2, 3, 4, 5. So 5.5 cycles. Divide that by 6 seconds and I get the frequency. If I want to get the period, I would take the reciprocal of that. So if I reciprocate that value, I get about 1.1 seconds. As you go through to do this activity, it's asking you to vary a factor systematically. So the first table, you might just vary the mass. The second table, you might keep the mass constant, but vary the spring constant. So vary the stiffness. I doubt you're going to have time to test the third factor, which would be the damping. So in reality, the amount of time that we have, you're probably just going to do factor 1, factor 2, is changing the mass and then also changing that spring stiffness. Okay? Questions for me? You should be able to get this done before you leave today. You have about 20 minutes. Enough time to be able to complete this. Give it a go. If you're trying this from home, make sure you obtain that sheet.